Good afternoon, everybody, and it's my pleasure come to City University of Hong Kong to share some of my research and also yeah. Okay, today I'm going to talk about advancing understanding in carbon mineralization for low or negative construction materials and products. And you all know, this is a very, very hot topic at the moment, and you probably have read a lot of papers. But on the other hand, I think there are still a lot of scientific tricks before those papers. And well, phenomenally, it seems kind of very simple, but on the other hand, the process is very complicated. And also, especially for sampling and testing, it involves a lot of cares and also scientific understanding of the processes. And well, I give you some quick idea where from Changsha and Hunan University. That's why yes, and well now direct high-speed train and less than 3 hours, and so it's very easy. I think some of you have been visited, Hunan University, and also some of my students are here, and well. Hunan University and what dates back to 976 AD, which was the Royal Academy founded. And well, actually, this year we are celebrating 1050th anniversary of the academy, and we have 30 colleges, departments, and one graduate school, and we have almost 40,000 students now, and including 21, undergraduate students. And well, depends who ranks, and this year, and U.S. News ranks Hunan University as number 11 in China and number 19 globally by U.S. News. I think a city in Hong Kong ranks like 60 or 70 or something, yeah, like that, right? And well, then come to civil engineering, and while we celebrated the 120th anniversary a few years ago, and well, several ranking and ranked civil engineering at top 5 in China, and we have 10 departments, including one department of building materials, and well, actually, this is also the ranking from organization in China ranks number 6 in the world and number 5 in China. And so you can see, we do have very good research program there. And well, actually, those are the departments within the college, and we also have several key laboratory. And actually, I'm the director of 3 key laboratories there. And so, yeah. Well, for my research group, and we mainly focus on 4 areas, and how to enhance the performance, and also endorse the functions for civil engineering materials, and also try to develop a low environmental, load construction materials, and finally, we mainly work with other areas like structure, geotech, or even building physics, how to apply or develop the materials. And well, actually, this is a research areas we are mainly working on currently, including the design and microstructure and the performance of cementitious material, and how to use the byproduct waste material and carbon mineralization and HPC and EHPC, and also modeling simulation and cement and concrete admixture and self-healing, self-sealing, self-healing liner, and etc. So basically, we cover from organic to inorganic, and from micro to macro level, and also from chemistry to mechanics, and from materials to structure, and yeah. And well, this is actually the group member, in our materials, and actually Nami Banthia at the moment is our affiliate professor there, and Professor Francis, and specializing, use of new materials in structure, and so then other people, and mainly specialize, pure materials, and um, well, relatively, for research group, we have quite good equipment or instruments. Well, actually, I haven't got CT picture. So in my own lab, and we have CT, ACM, XRD, NMR, and basically all those basic toys for similar concrete testing. And so if you read our papers, basically from maybe TM and also solid NMR for aluminum or silicon, usually send it to university testing center, but then all other testings are conducted in my own lab. Yeah, that's it. And mainly we have been working on several areas. One is the design of high performance or ultra high performance concrete with multiple performance targets. And before, when people design the concrete, usually they read the literature or, previous report, pick a few basic mixture and try to optimize or modify it. But on other hand, if you change some composition or change some parameters, the mixture will not work. So after actually I moved back from Canada, US to China, and I started to be in charge of one project for Changsha subway, and while I was appointed to be responsible for raw material selection and also concrete design for the subway system. And so then, should we, consider all this uh, requirements or performance targets during the mixture design? So then I started to think about it and then come up with this new approach. And first, we should try to use closer packing of aggregates because all those deformation or majority of durability problems are caused by cement paste. So we should try to use less cement and to have close packing of aggregates. Then in order to lubricate the aggregates to achieve certain workability or rheology, and so then we have to have some excessive cement paste. And so, yeah, that's it. Yeah, and third, then come to the binder composition, and before people just seems choose them randomly or just based on literature. And here we propose to use factory design, and I give you example here. Like if the binder consists of four components like cement, fly ash, silica film, and slag, and use this method and approach. And so then we could establish the mathematical relationship between the properties or quantitative microstructure parameters. Basically, anything that can be quantitatively described with the composition of the binder. And so third is, based on determining the binder composition and also your workability requirement. And so we try to use chemical admixture to adjust its rheology or workability. Because before people, if it's the workability or slump is not good enough, then they add more water or change sand to cement ratio. So that's not really a scientific way. And because now chemical admixture is well advanced, developed, and so we can use superplasticide to increase its workability or to reduce water demand, or VMA, viscosity modifier agent, to change its viscosity. And so then, and I give you, five ternary diagram here. And so because if we have the four composition and you will get the counter plane, not the curve, but majority cases, we usually use cement, slag, and flash. So here I use the ternary diagram as an example. So you can see we get the ternary diagram for compressive strength, for workability, for carbonation resistance, for shrinkage, or for alkyl reaction, expansion, whatever you have. So then we stack all this fiber, or even you can plot the cost, within the triangle. So then we stack the five triangle together. So then you can see, gray shadows. So this gray shadow areas give you the performance or the property requirement that meet all the specified number. So that's, how the approach I, developed. And so then also, we group also working on design high performance composite material, and actually Professor G mainly working on, TRC based reinforced cementitious material. And yeah, our third area is efficient use of waste material, including carbon mineralization. I will talk more detail later, and also, well, the activation of solid waste material. Well, actually, we here in the laboratory found out the relationship between the calcium to silica ratio and for the formation of either CSH or CaSH. And yeah. And also we use a chemical activator like sodium carbonate, sodium hydroxide, and sodium silicate to regulate the setting and property development of alkali activated material. So that's kind of a topic we have been working on. And also, we have been using our research achievements in the application or construction of like a Changsha subway system and also several bridges. And well, actually, especially, I want to mention Tanglong Bridge in Hanoi, Vietnam. And well, actually, they sent delegations to our university several times to learn how to design UHPC and also how to construct the UHPC overlay system. And well, that bridge before basically carries almost 50% of transportation in and out of Hanoi. And before the renovation and retrofit, and the bridge can take only about 10,000 vehicles per day, and at a speed of like 10 or 20 kilometers per hour. But now you can drive on at like 100 kilometers per hour, and it can carry over 10,000 vehicles per day. And so last year, Raleigh Convention was held there. And so I went to the site to visit the bridges there. And also there are some other applications. Well, actually, we also use this approach for ready-mix concrete company to help them design the concrete mixture with better performance, but even lower cost. And And also, as for UHPC, you probably have read some reports, and Hunan University have been involved with more than 200 UHPC bridges in China and overseas now. Yeah, that's it. And so, yeah, we have published, over 1,000 papers with more than, actually, probably 90,000 citation, not 80,000. And actually, we are also publishing a lot of textbook and technical books in the materials area. And yeah. And yeah, we have organized 4 international courses with RILEM and also 2 line public courses on civil engineering materials progress and also the testing methods. Yeah, we have had over 500,000 audience from all over the world. I'm not sure, probably some of you here also have listened to our online courses. And this semester, and we have a break, and but yeah, next semester we will continue the courses on the progresses in new synergy materials, and we invite all those very famous and well experienced professors or researchers to talk about this new materials and also the testing method for civil engineering materials. And Yeah, we have also launched and organized five series international conference and two series domestic conference and on different subjects. Yeah. And yeah, we have given a lot of talks all over the world, and especially in similar concrete area, there is a very famous or the largest conference is called the International Congress on the Chemistry of Cement, and I have been invited to give four consecutive keynote lectures. Actually, next one will be in New Delhi and Indian, and yeah, I have actually I'm being preparing the fifth keynote presentation for the Congress at the moment. Yeah, and yeah, also launched a journal and a journal for sustainable cement-based material in 2012, and it has an impact factor of 4.2. It's a traditional journal, so no fee at all. And but on the other hand, our rejection rate is about between 95 to 80%. So we welcome, high quality manuscript, and yeah, that's it. And now, yeah, let me back to the technical topic, yeah, about the carbon mineralization. And well, actually, oh, sorry. I also would like to mention, and well, our actual book just released, Carbon Mineralization for Construction Materials and Products, and published by CRC Price. And so, yeah, if you're interested, and yeah, you can buy one from internet. And I think this is the first. Written book. Well, I was involved in the editing of two books, but that was launched by Fernando, from Portugal, and well, that book, basically two versions were written by a variety of authors. Maybe you are Xianping, yeah, was also involved, right? So it's not that systematic, and but here, yeah, basically, myself, my student Xiang Hu, now he's also associate professor at Hunan University, and also my PhD student Yu Guangmao, and so we wrote this books together, and so yeah, and yeah, so this is outline of my talk, and first I would like to go give you some background information about this topic, and oh, okay, we all know, during past 2 decades, and the greenhouse gas effect become, more and more obvious, and the CO2 concentration in the air continues, to increase. The atmospheric temperature also continue to increase. The sea level is rising, and now we have seen a lot of human health problem, and we also get more and extreme weathers, and the acid, the oceans become more acidic. And well, because in civil engineering, our main basic material using is cement, right? So this is a basic, flow chart of Portland cement production, and so you can see during the production process, and first the limestone and the clay getting dried between 100 and 200 degrees C, and then dehydration of clay, and so then decomposition of limestone, and finally the clinker mineral will form between 1012 to 1500 degrees C. So you can see, it involves very high temperature, and well, but on the other hand, during the production, it consumes about, 1 ton for clinker consumes about 1.4 tons for limestone, and 100 kilo of coal, and also, well, 860 kilo of CO2 for advanced conventional bottle cement production line. But now people are try to use more and more alternative fuels or more waste material to replace limestone, or, other raw materials. The release amount will be less. And well, if we look at the process in a very simple way, and so basically you can see is mainly due to the reaction between calcium carbonate and silica to form dicalcium silicate plus release CO2, and then tricalcium silicate plus silica and form tricalcium silicate and release, carbon dioxide. So those reaction happens mainly between 1,200 to 1,500 degrees C. So, chemically also thermodynamically, the opposite reactions can happen very easily at room temperature and even can release a lot of heat, right? So, all conventional concrete basically is mixing with, cement with water and to get hardened concrete. And so basically we should try use the reverse of cement production to, consume carbon dioxide to get limestone. And this is basically give you some, information about the carbon dioxide release from cement industry, and also, the right two charts, the top one is actually from the Chinese cement industry, and in order to reach net zero, and so they estimated about 36% of CO2 released from cement industry that need to be captured, either stored or mineralized for use. And in China, at the peak time period, it released about 1.5 billion tons of CO2. But now I think, the cement production is less and still probably near, 1 billion tons of CO2. And the bottom actually chart is from Global Cement and Concrete Association, and by their estimation, and although we try to use much efficient cement production process and use more, byproduct and waste material, and also, try to increase the durability of concrete by the end, also still about 35% of CO2 that has to be captured, either to be stored or carbon mineralized. And this was similar concrete industry. So, yeah. So, this is basically, the common flow chart for carbon capture, utilization, and storage. And so you can see, this is captured CO2 either to be stored in this discarded, oil well, or in the ocean, or biological method, or industry uses. But on the other hand, come to industry uses, the quantity is very limited. And I did some information search, and even for like Shanghai City, and it used about 200 or 300,000 tons of CO2 per year. So you can see, the industrial or the commercial use for CO2 is very, very limited. And then as for this topic, and so at the 15th International Congress on the Chemistry of Cement, which held is in Prague, and I was invited to be in charge of the topic on, low carbon binder materials. And it covers three topics: alkali activated material, carbonate binder, and also, belate based binder. And I invited John Prof to write the part of alkali activated material, and I wrote the carbonate binder and give the presentation there. So at that time, there was only one keynote presentation and 15 regular presentation related to carbon mineralization. But on the other hand, in 2023 and 16th International Congress on the Chemistry of Cement held in Bangkok, Thailand, and it had 4 keynote presentations, and 95 out of 500 presentations regulatory related to carbon mineralization. So you can see, this is a really hot topic in similar concrete materials area. Now let's have a look of scientific base on basically thermodynamics for carbon mineralizations of some materials. Well, actually, here you can see some charts there. The first one is basically the conventional hydration or hardening of concrete, similar clinker with water to form a calcium silicate hydrate and some other hydration products. So the second one actually is the clinker and carbonated directly and but in the presence of moisture. So then we mainly got a calcite and also some silica gel. And the third one actually is hardened concrete or mainly calcium silicate hydrate and react with carbon dioxide and so then also form calcite and CSH and some leftover and also plus silica gel. And so when we did some thermodynamic calculation, and you can also see, tricalcium silicate, dicalcium silicate, and also, monocalcium silicate, tricalcium aluminate, and all those hydration or non-hydrated calcium silicate can be carbonated automatically, right? And during the carbonation, actually, we can get four polymorphs of calcium carbonate, basically amorphous and a cubic calcite and a prism, aragonite and also spherical vetrate. And so then if we divided all those carbonatable raw material and basically they are colorless material, basically, calcium silicates and also calcium aluminates. And so then magnesium-based material and also those industrial byproduct and waste material. And basically all of them can be thermodynamically carbonated and then mainly form calcite, aragonite, or vetrate plus silica gel. And let's have a look of first, okay, how can carbon dioxide react with CO2, calcium oxide, and also calcium hydroxide? Well, thermodynamically, even under dry condition, and you can see the Gibbs energy for both the carbonation of calcium oxide and also calcium hydroxide, you can see, they are very negative. So this means they can happen, very easily. But on other hand, their reaction rate and dry conditions are extremely low. Well, one actually other good example is, what we see every day, the window glass. It's glassy material. And thermodynamically, it's also unstable, right? And but on the other hand, even after hundreds of years, they were not converted to silica, right? And so it's the same like this. And so then even all those calcium silicate hydrate, and you can see they free Gibbs energy almost between minus 26 to almost minus 95 kilojoule per mole, and they're also very negative. But on other hand, in the dry condition, they also carbonated very, very slowly. So this means moisture or certain amount of water is very important or even critical for the fast carbonation or carbon mineralization. Well, also even supersaturated solution of calcium hydroxide, calcium react with carbonate ion, result in the precipitation of amorphous calcium silicate, even in the presence of moisture. And so then you can see initially it will form amorphous calcium carbonate, and then with time, the crystal sizes of calcium carbonate start to grow. And well, as I mentioned earlier, actually, calcium carbonate has three polymorphs. And I mean, crystallized. It has cubic forms. And but on other hand, if you look at the density, especially, and the cassette, is about 2710, and then aragonite is 2930, and then vetrate is about 2540. So they have very different polymorph and also have different, density. So during their formation, actually, it will affect the property of final carbon mineralized product significantly because the cubic calcium carbonate could have high compressive strength, but on other hand, it's very brittle, just like a marble, we have seen easy, during that time, right? They, and then also aragonite, it has a needle structure, and well, actually the typical example is seashell. Seashell consists of mainly of aragonite. So it also has very good flexural strength and ductility. And so vetrate and is very unstable, but on other hand, it has ball structure and it may improve the workability of the concrete, and especially it has low density and it may increase the complexity or density of the concrete material or the lower porosity here. And well, so how we can really control the formation of different calcium carbonate. And so first, thermodynamically, we establish a model and then try to add different additive or the changes in environmental to, try to get different polymorph of calcium carbonate. And so then we found that when we add some inorganic additives such as metal divalent ions, like, magnesium and zinc, that they can control the formation of calcium carbonate by changing the solubility or crystallization habits of calcium carbonate. And we also tried some organic additives such as MEA, EDTA, and PAA. They can control the formation of calcium carbonate by selective adsorption to change the surface energy, then get different polymorphs. So, those thermodynamics can really help or guide our research and to achieve, different results. Well, this actually is a comparison between, our model with the published result data, and you can see for, magnesium chloride concentration, our model fits the experimental results very well. And also as for temperature, you can see, from 60 to 80 degrees C, and the aragonite start to form, and when it's over 90 degrees C, and you will mainly get aragonite instead of calcite. So yeah. And so then you can see when we use, different organic additives such as PAA, PAM, and PAV, and so you can see, our model also fits the experimental results very well here. And yeah, so then we also try to understand the carbon mineralization of magnesium silicates. Well, actually, quite a lot of work have been done or have been published by geologic people. And well, initially, they tried to carbon mineralize or mineralize the carbon through the reaction between carbon and oliva and also some other like basalt material. But on other hand, the mineralization of those materials, using those materials, you need to have very high pressure and a very high temperature. And so, well, there are some actually processes, they basically, can change the, magnesium silicates to, or basically convert them to magnesium oxide. So then they can be carbonated very quickly. So yeah. So also you can see magnesium silicate and also magnesium silicate hydrate, they gives the energy for carbonation are also very negative, but on other hand, they can also not be easily carbonated at room temperature. And so, yeah. And so now we'll also look at the historic development of carbon mineralization technology. Well, and well, when I started this project in 2002, 2003, and so I did the patent search, and they found, well, even in 1870 and 1872, first two patents were granted to James Lowland, and he tried to use carbon dioxide to accelerate the setting and hardening of concrete panels and also other products. But well, then I did some, more detailed research, and then in 1972, and some research people at UIUC did some combination of calcium silicates, including calcium silicate, beta, dicalcium silicate, and also gamma dicalcium silicate. And but they did not try to, produce any products. And well, actually, then in the 90s, and quite a few companies in Europe tried to use this technology, carbon mineralization, to accelerate the hardening of cement wallboard. And because at that time, the chemical admixture is not well developed, and so the production of cement wallboard need a long time for the setting and also large space for the initial curing and stockpile. And but on the other hand, then they found although the surface of the concrete can react with CO2 very quickly, but on the other hand, the reactions can happen mainly at the surface, cannot go inside. So then, 2007, yeah, we published first paper or, our results. And so then Solidia, well, basically US company, yeah, and they played some, game and tried to get, some patents, use so-called Solidia cement, which consists mainly of monocalcium silicate and tricalcium silicates, and then to carbon mineralize it, basically use my invented technology. And well, the reason, because I have published quite a few papers, on the carbon mineralization of conventional Bhutan cement. So in that way, they cannot really play, or they cannot get a patent. Well, so later on, we worked with Hong Kong, Polytech, and also my group have invented how to use CO2 to convert the waste hardened cement paste into reactive supplemental cementitious material, and also use CO2 mineralization for concrete surface treatment. Well, then in 2021, we built the world's first real carbon mineralization plants. Okay, so that's not a post, okay. Well, so now let's have a look of carbon mineralization of basically calcium-based material. Well, this is our concrete mixing. Basically, is cement aggregates, supplemental cementitious material, water, and a chemical admixture. Well, mainly we can see two types of concrete. One is highly flowable concrete for either ready mix or in situ casting products, and like the top picture. And well, the other one is dry mixture, and mainly for masonry bricks, blocks, and also some other products like paving stone. And well, initially when I started working on this project, I thought, well, block looks very porous and rough, right? And so I think CO2 can go inside very easily, but actually it doesn't. Because in order to get the whole piece compacted products. And they have to use proper water-to-cement ratio and compaction pressure to ensure all the voids within the products filled with water. So then you can get a whole piece of a product. Otherwise, it will fall apart. So in that case, CO2 can still not go inside. So that's how, this figures demonstrate, my initial testing. And so we compacted some small cylinders, use the block mixture, it's very dry. And so then expose it to CO2. And so then you can see, only the surface carbonate. And so then sort of, after the molding or compaction, how can we really remove the moisture in those capillary pores? Because, without moisture, it's a very porous mixture. So in that way, we can let CO2 to go inside very quickly, right? And so then we developed preconditioning. Well, initially, basically, we proposed this concept, and then we developed this technology. And so you can see, okay, after molding and casting, and we try to remove some moisture, and so open all this continuous channel, and so then inject CO2, and so CO2 can go inside those channels very quickly, right? And so basically, the left picture shows, well, actually, this is already as flow chart in their marketing flyer document. So basically, they use the all idea and concept for that process. And so now the next question is, how much moisture we should remove? Because as I mentioned earlier, if it's really dry cement or even dry lime, the reaction with carbon dioxide is very, very, very slow. And so then in laboratory, so we controlled the relative humidity during the preconditioning process. So you can see relative humidity from 80%, 60, 70%, 35, or 45%. And the left figure shows the moisture loss. And so you can see, the 60, 70%, they remove about 20% of moisture, for that, dry mixture. And for 35 or 45 relative humidity, it can remove almost 80% of moisture, right? And the 80 relative humidity percent, it will remove only about 5% of moisture, water. And so then if we look at the right figure, which shows the carbonation degree, which is defined as the percentage of carbonated cement to the total cement in the sample. And so then you can see, if we look at the green line, which was conditioned at 80% relative humidity, and so you can see the carbonation degree reached only about 10%. And but then for 60, 70% preconditioning, and so you can see initially the carbonation degree increase quickly and then reach a plateau. And but for 35 or 45% relative humidity preconditioning, and in very short time period, it can reach a high carbonation degree. But on the other hand, as the preconditioning time increases, then the carbonation degree drops very quickly, right? So for the real uses or for real production, I think, 60, 80% relative humidity preconditioning is the best rhythm. Well, so now when you look at the publication, well, probably a lot of people say, oh, yeah, let's dry and remove 20% mulch. But actually, well, our late paper, we are not published. We are still doing more research because for different raw materials and the preconditioning or the reminder moisture is different. And um, well, the other thing is during the carbon mineralizations, as I mentioned earlier, it releases lots of heat. And because, the clink minerals were formed at 1,200, 1,500 degrees C, right? So basically, it has very, very high embodied energy. And so you can see here, the left figure is a temperature profile of the specimen as in 3 locations. Well, if, okay. Okay. If you look at the CO2 cooling chamber, you can see 3 temperature sensors. One is inside or in the center of the sample, and one is outside surface of the sample, and one is on the surface of inside the chamber. Okay, so then here the recorded temperature. Okay, the black line is inside of the sample, and the red line is the surface of the sample, and the blue line is basically inside the surface of the cooling chamber. So you can see almost basically at 15 minutes, this 5-liter container with 4 samples, the temperature here reached about 45 degrees C. And the next one, the right one, even reached over 60 degrees C. You can see how much heat, even within 50 degrees C, right? Within 15 minutes. Because if you really measure the carbonation degree, and within 15 minutes, the carbonation degree is also relatively not that high. And well, so then we measure the strength of the sample. And so you can see if we did not really precondition a sample and then with CO2 curing, yes, it also gives some strength. But on the other hand, compared with the right figure, and the right figure is basically is within 2 hours up to 18 hours of dry preconditioning of 2 hours. And then we inject CO2 with a pressure of only 20 psi, almost no pressure. So you can see after 2 hours of preconditioning, then 2 hours of CO2 curing, the sample gives strength almost the same as the right bar, and that one was cured for 20 hours at 80 degrees C. Okay, so you can see here preconditioning is very critical to reach high strength and also, of course, high carbon mineralization degree. Well, one thing here, well, actually, I haven't published this results, and well, as I said earlier, in our experiment, we found remove about 20% of moisture gives the best results. And so here, based on this equation, we can calculate the relation, the relative humidity corresponding or corresponded pore diameter. So 30% of related humidity corresponds to 2,000 to 3,000 nanometer pores in diameter. OK， 不从阿这看的又是 molecular dynamics. You can also calculate what's the surface layer thickness of water on the flat particles surface. But on other hand, as I said, for different material, raw material, or even different pore solution, so then the surface tension, the gamma here, will be also different. So this means, it's not just simple, I remove certain moisture through drying, but I think scientifically, you probably should really try to do more measurements, understanding the relationship between pore diameter and the related humidity, and then to get a clear explanation of carbon mineralization. Okay, so this is it. Well, so then we also carbon mineralize some concrete blocks, and so for simple curing and moisture curing, we put them in the plastic bags, spray some water, and so keep them in a certain time period, and so then we can see, and after carbon mineralization, you can see the strength continue to increase, and especially the top this bars actually, this is immediately after 2 hours of carbon mineralization. This is actually after 24 hours of steam curing, and so then the further moisture curing to up to 28 and 90 days, and then we can see the strength of the block continue to increase significantly, because as I mentioned earlier, the carbonation degree of cement inside the block was only about 25%. Now we can reach 50%. Okay? So still, 70% cement uncarbonated inside the block, continue to hydrate and so continue to enhance the property of the blocks. Right. So that's cool. Well, so then we also exposure the blocks into the wind freezing soil and winter weather condition, and so you can see actually there is no difference between the carbon mineralized product and the steam cured, and so actually this the black bar is steam cured, and this gray bar is carbon mineralized bricks, right? And so there is no difference between strengths and for them. And but on the other hand, if we look at the dry shrinkage, and here, and this is steam cured, and this is carbon mineralized block, and so you can see carbon mineralized block give lower shrinkage than the steam cured blocks, right? And sorry. Well, actually, if we look at compare the strengths, actually the first one, this relationship from the literature, and shows the carbonation degree and the compressive strength, because different people use different mixture and different compaction pressure, and even you can very easily to reach like 200 or 300 megapascal, and if you compact the specimen with like 200 or 300 megapascal pressure, right? And so and but on other hand, if we look at this the bar here, and only with 1 days of water curing, or then 20 actually 2 to 28 days of water curing, and this one is 2 hours of CO2 curing, and then 27 days of moisture curing, and this is you can even see the initial carbon mineralization can give even higher strength than water-cooled standard concrete. Okay. Yeah. And well, the other interesting thing in carbon minerals product is silica gel. And well, Solidia actually copied my idea and tried to market the technology. But on the other hand, there are very serious issue with their process. Now they changed the marketing strategy. Now they try to produce solid cement, then carbonate it and sell it as supplemental cementitious material. So I kind of understand, use such a high temperature, such a complicated process, and then to produce a supplemental cementitious material, not cement. Well, the reason is for solid cement, they use very low calcium there. So after carbon mineralization, they got a lot of silica gel. And if you have worked in chemistry lab, we all know we often use silica gel as a drying agent, right? Even actually now, when you buy some, good stuff and or some foods, they put some dry silica gel inside the package as a drying agent, right? But on the other hand, if dry silica gel is exposed to moisture, so then it will expand, right? So this means such a kind of a product goes through wetting and drying process. So then will cause shrink, expansion, and so then we deteriorate, right? That's one thing. The other thing is because their main minerals are monocalcium disilicate and tricalcium disilicate, those two minerals cannot react with water. So once carbonation is finished, their property or microstructure reaches the peak. So then when you start to use it, the material will deteriorate very quickly, right? So here, I think it's also very important to understand how the silica gel form and also how the silica gel behaves later on, because when you use some carbon mineralized product or carbon mineralized material as a supplemental cementitious material, it will also involve a much more complicated process. So anyway, so you can see here, and here in cement clinker, you mainly have mono silica gel, but so then, well, basically Q0, Q1, but then after initial carbonation, you will get some Q2, Q3, and so then as the carbonation times increase, so then you will get a much more polymerized silica gel. So this is, why I said, it's very important for later on how are we going to use this carbon mineralized product. And well, this is also some SEM picture shows, okay, this shows the, product before carbonation. And if we leave the specimen in moisture condition, and so then we can see some crystallized hydration products. But then if we precondition them in dry environment, we can also see some hydration product, but not much. But so then after carbonation, and especially the one after, the dry preconditioning, we can see a lot of, calcium carbonate formed here. And, sorry. Well, as I said, at the moment so far, we can get only 50% cement carbonate. So this uncarbonated cement will continue to hydrate in most environments. So you can see a lot of semi hydration products, especially like this typical, jet formed, in the product. And so. Well, another thing is, people start to concern how the carbon mineralization affects the alkalinity of the product or the steel corrosion, right? And so this first big figure, is a relationship between compressive strength and the carbonation degree. And so then we measured the solution, post-solution of the carbon mineralized product and then, hydrated. So you can see in the middle figure and without the carbon mineralization, it can give you pH about over 13. And but on the other hand, if we carbon mineralize the sample for several hours at beginning and then hydrated, and so you can see the pH is above 11.8. And usually, when the pH is above 15 or above 11, so the passivation for layer will form at the surface of a rebar. So in that way, you can, you are sure carbon mineral product will not cause the steel corrosion issue. Okay. And but of course, the higher the initial carbonation degree and the less the hydration degree and all the chemical combined water, and so that's we can understand. On other hand, and after carbon mineralization, initially we can measure or we can find silica gel form, but on other hand, as we immerse the specimen in water, and so later on, actually, silica gel will disappear. And because, the cement hydration will release the calcium hydroxide, right? Calcium hydroxide will react with silica gel, form calcium silicate hydrate. So this will be similar to, conventional bottom cement. Yeah. Well, the other thing is the polymer for control, and here I show you some results with 10% magnesium hydroxide, and the left picture shows the control batch, so you can see we mainly get a cassette, but on other hand, the right picture, after we replace the cement with 10% magnesium hydroxide, we got mainly aragonite. And so what if we look at the strengths and the left figure and these compressive strengths, you cannot see the difference. But on the other hand, if we look at the right side, the fracture strengths, and actually this the right bar here, the right bar, this is the strength of the sample after 28 days of water curing. And on other hand, we can see, after 3 days of carbon mineralization, they give the same strength as, 28 of water curing, right? So then we increase the CO2 curing time up to 7 and 28 days. And so then you can see both the compressive and the fracture strength is become significantly higher than the water-cooled specimen. And but on the other hand, especially we can see when we increase the magnesium hydroxide content from 0 to 10%, the fracture strength increase from about 8 meg to almost 14 to 15 meg per second. This is about 60 or 70% more than the control batch. So then you can see it will greatly increase the flexural property or the ductility of the material here. Yeah. And also want to show you some results how we use carbonation for the surface treatment of concrete products. And so here we cast some cubes and cylinders, and so then we use CO2 surface treatment and for strength testing and also for water vapor adsorption testing and also chloride migration testing here. And so this compresses So strength follow as TMC, C109 should be, and also water absorption testing as TMC 1585, and also water vapor transmission test results. And okay, this figures show you, quite a lot of interesting results here. Okay, so for the surface treatment, the left figures, and so you can see here the control batch, and after 3 hours of combination and after 6 hours of combination. Okay, for those specimen, we cast the specimen and then demoted the next day, and exposure to the relative humidity of 60% only for 1 hour. And so then you can see the calcium carbonate content from the surface to inside. Well, we developed a special machine to get a very thin layer of sample. You can see here the thickness we got is every 0.2 millimeter. Well, probably I can say, so far, probably the only, such a thin thickness, right? We have taken in the publications. Well, but so then if you look at the calcium hydrocarbonate content changes, so the surface, the top one, the bottom, okay, the top one is for water simulation of 0.3. The bottom one is for water simulation 0.4. And the bottom one is water simulation 0.4. And so the initial surface content almost 45%. But the thickness is only about what? 1.6 millimeter. Become basically, uncarbonated. So here, what I want to point out here. So when you guys read the papers, you might want to think about how did the author take the sample? Because usually, we use a hammer, right? Break a sample. And I think even probably you got a 5 millimeter thick of chunks. You think it's very small. But so you can see here, if we use even 1 or 2 millimeter sample thickness to measure the results, what kind of results you will get? Okay, so I threw this question to you. So later on, when my students do some, experiment, I have to ask him to ensure from the surface to inside, from one side to other side, that has to show the similar results. The same results. Otherwise, if you get a chunk, it's not a representative result. Right. And the second figure is the compressive strength, as we expected, because the carbonation thickness is very thin, very small, so it only slightly increases the compressive strength. But on the other hand, if you look at the third one, this is water vapor, diffusion coefficient. So the top line, the blue line, is the control batch, and the bottom line, is after 90 days of, further cooling. So you can see even only 1.5 millimeter of initial carbonation, it decreases the water vapor penetration coefficient almost 75%. Okay. So the next one, water vapor permeability also show you the similar results. And this actually is the cylinder we used for chloride migration coefficient test. And so you can also see, after 6 hours of carbonation, the chloride migration coefficient decrease more than 50%. So this means, initial surface carbonation is a really, really excellent method to enhance or to produce integrated impermeable surface. Because, you can see in many cases, people use coating, to coat the concrete surface, right? For inorganic coating, after a certain period of time, it may peel off. And for organic, it will deteriorate and also peel off. But this is become a part of the concrete product itself. So it's, very reliable for a long time, right? So you can see, yeah, this is it. Well, and also, if we combine, conventional Portland cement and also the solid technology, and we think we should use, low calcium clinker, but on other hand, the mineral will be sure to be the beta dicalcium silicate because beta dicalcium silicate can be carbonated very quickly, easily, but on other hand, it also has low hydration property because later on, after carbonation, it will continue to hydrate and enhance the property rather than like a solid cement. Once carbonation is finished, it reaches a peak and it starts going down. And so, okay, we did some laboratory batch at Hunan, Polytech University. And so you can see we use the material and the design as a dicalcium silicate and, passing it. And okay, the tricky is here, the cooling process. Okay, if we cool it very slowly, we got mainly beta gas and beta or gamma dicalcium silicate. It has no hydraulic property, or it cannot react to or hydrate with water. And but here we try to control get 85% beta dicalcium silicate. So later on, it will continue hydrate with water and further enhance the property. So you can see here, and we can choose the cooling, and then you can see the cement particle we got here is about 20 micrometer, is only slightly coarse or than Portland cement. And so then we carbonated it, and so you can see what the strength property also develop very well. And what actually we calculate the energy consumption and CO2 embodied CO2, and this property is basically reduce almost 50% energy consumption and CO2 release compared to conventional bottom cement. Well, now we are still working on this, and because actually the cooling process is not so easy to control, and but on the other hand, because Portland cement production is well established, and so the process can be well controlled, and well, so now we also, now a lot of people are working on the carbon mineralization of industrial byproduct and waste material. And well, actually, this is the information we compiled from literature. And, fly ash, similar clinker acid, and blast furnace slag. And so some of them also give the maximum CO2 uptake. Okay. Well, here, I want to point out this maximum is a very theoretical value. And actually, the calcium oxide in glass material is not so easy to be carbonated. Well, the window glass contains about 10% lime and 13% of sodium oxide. So as I said, even after 100 years, you can see, the glass never get carbonated, or the carbonated layer could be very, very thin. Okay. And well, initially we did some work and it didn't work. So I put it aside. So actually, recently some paper, from Tongji University, Jiangxing with group. And so what I can, well, probably should you first graph shows basically how the calcium silica ratio affect, the carbon mineralization. And so you can see if the calcium to silica ratio is very low and the carbon uptake is also low. And but on the other hand, if increase the carbon calcium to silica ratio, and then carbon uptake is increased. And but on other hand, well, those are the glass material. And but on other hand, if you compare, this is the calcium to silica ratio 1 glass, and this the bottom figure is actual wollastonite, and this is a crystallized calcium to silica ratio 1 calcium silicate. But on the other hand, you can see, the carbon dioxide uptake is become higher. Okay, well, actually, the other very interesting results is aluminum. Okay, so you can see the first figure is, Ca point 1 and S. And this is the last figure, it contains more aluminum. So you can see, here, the carbon uptake become very, very low, right? And, well, basically, chemically, they explain without aluminum, the slag will be uniformly dissolved, and so then those calcium ion can react with carbon and to form calcium carbonate uniformly on the surface. But on the other hand, if aluminum exists, so then the surface cannot be uniformly dissolved. And so then it dissolved in big chunks. And so only small amount of calcium ions dissolved into solution and to react with carbon dioxide to form calcium carbonate. Well, but those are very, very rough mechanism. I think there's still a lot of scientific study needed to really understand, the mechanism here. Well, actually, my students also did quite a bit of work on this topic. Okay, we tried initially to carbonate blast furnace slag in bore mill. And so you can see we use weight bore mill 1 hour, 2 hours, 3 hours, and then also at 40 and 60 degrees C. And so you can see the weight loss or the calcium carbonate formed is only 1 to 2%, right? It's very small. And so then, and SEM, we can see, this is original slag particles, and this is after, 2 hours, and this is after 3 hours, and this is after 2 hours at 60 degrees C. So you can see, the surface carbonation is very, very limited, right? So you can see, this is really, really interesting. It is yeah, we also working on that. So I think, it's also a good topic to try to understand because, it involves like a flash, blast furnace slag, and some other glassy material, whether they can be really used for carbon mineralization purpose, or how can we really improve the carbonation efficiency, very scientific. Okay, so that's it. Okay. Well, this actually published results, they said, they use high calcium flash, but on other hand, you can see they use a temperature of like 200 or 160 degrees C. And so then probably also that's why they cannot really get good results at room temperature, right? And yeah. So, well, the other exception actually is steel slab. Steel slug is not what we call it a slug, but actually it's not winter culture or fast cold. Usually they cool it, pull the slug onto the ground, or now, well, actually some Chinese company develop a process, pull it down in a big steel pan and let it cool slowly and then spray some more water on. And so then, the big chunk will break into small pieces, right? And but on other hand, steel slag consists mainly of different minerals, as listed in the table, and thermodynamically, all those minerals can be carbonated very easily. And well, actually, those work are from my friends, Professor Caijun, and now he's a professor at Hunan University. He studied how the particle size and CO2 concentration and temperature affects carbonation and well, actually, and he, tried to directly carbonate it to make steel slag products. And so you can see the strength here he got is about 60 degrees, 40 megapascal. Well, recently, I also have been collecting quite a bit of information. And well, probably later this year, I will give a talk on how can we really use carbon mineralization technology efficiently. Because the, let me see. Oh, I didn't put it. That's slide on. Because now a lot of people try to carbonate steel slag to make lightweight aggregates. Okay, steel slag has a density about 3.8 or 3.9. Okay, limestone or regular coarse aggregate has a density of about 2.6. And so you try to use such a heavy material to make lightweight aggregate. Okay, that's one question. Second is, yes, now also a lot of people try to carbonate steel slag to make supplemental cementitious material. And because it can be carbonated to make a product directly, why carbonate it to make supplemental cementitious material? Well, the one slag, well, the reason is, well, one of my PhD student has been working on his thesis 7 years, and well, at that time we started working on steel slag only like I don't know 2, 3, or 5 papers on this topic, but now probably thousands. And but he did got some very good results, and we threw some chemical admixture to enhance the carbonation, and we can get the strength of 60 to 70 megapascal, to make carbonated steel slag product directly rather than, carbonated to become the supplemental cementitious material. Okay, so the other material is recycled concrete fine. Well, actually, I just recently graduate PhD student. Now he's a postdoc at Imperial College, and Well, within 2.5 years, and he published three CCR, three CCC, and also several other journal papers on this topic. Well, this is project was supported by Global Seminar Concrete Association, and so yeah. Well, first, actually, part of his interesting work is he quantitatively calculated the different effects of carbonate recycled concrete fine as a supplemental cementitious material, including the filler effect, pozzolanic effect, and also what's that, like basically he calculated 4 or 5 effects, and so then also how do they contribute to the strength, and so which was published in CCI. Well, the other process actually developed by Maruyama Impa, from Tokyo University. So they use basically here the container filled with recycled concrete aggregate. Sorry, here recycled concrete, and so right, this is container. So they pump the calcium hydroxide solution and also CO2 here, and so then carbonate the recycled aggregate here. So that's their process. Well, so actually, we just one for my well, actually, 2 master students they work on. So I said, well, why don't we just compact the recycled concrete fine to make a product directly? So you can see here, after a few hours of carbonation, it reached very high strength. And well, even also very high, carbonation degree. You can see here, well, after basically a couple of days carbonation and reached about almost 70% carbonation degree and strength over 40 megapascal. That's strong enough for make a lot of construction products, right? And this paper actually recently published in CCC, and so I don't know why it did not show up as a. Oh, I cannot see this on this screen. I think the the publication information here. Yeah, just it just released, I think, last issue, and yeah. So that's why I think when next time I give a talk, I will raise this issue how we can really think those efficient process or technology really to directly make a product rather than to go a big circle and by the end you still cannot get a really good product, right? So and yeah, also some technology demonstration application. Well, first for our preconditioning technology and carbon mineralization, and we after almost 20 years of laboratory research, then we worked with Huaxin Cement Company in China. We built the world's first carbon mineralization concrete brick production line. And this plant produces 200 million pieces of concrete bricks per year. And so what the other amazing thing is here, we use cement flue gas, not the pure CO2. Because when you capture and purify CO2, it will cost about 6 or 800 RMB per ton. But here, well, actually, it also can purify the flue gas because we haven't measured, but on the other hand, you can see here we do not use any pressure, and basically flue gas flows through, and so you can see inside there are so many bricks stockpile inside, and the flue gas goes through. Definitely, some particles hit the bricks will precipitate, right? And that's the basic physics. So, well, anyway, so in 2021 December we had global news release, and so then a lot of cement companies and concrete manufacturing in the world start contact us. But on the other hand, you know, our university cannot really handle the international contract, and so I got stuck, by several projects here. And anyway, I think we will move forward with this, and especially with this production line, we have collected a lot of information and data, and for many other different applications. And well, of course, during past several years, and we measure the carbonation depths because thickness of the brick is 50 millimeter, and so half, is about 25 millimeters. So you can see, the majority of them reached about, on average 20 millimeters, something like that. The strength is about average 17 megapascal, and the Chinese standard require, minimum 15 megapascal. And so then we also stockpiled several bricks, outdoor, indoor, and so you can see the strength of the brick continue to increase. And so this plant basically consume about 60,000 tons of CO2 per year. And on other hand, originally it used high temperature steam autoclave, so we can save those steam for autoclaving, and which is equivalent to 8 million kilowatt electricity. So, it shows very significant environmental and technical advantage for this technology. Yeah, we have had, several certified testing reports. And so, yeah. And well, those bricks have been, used for a variety of projects. And so, yeah, they work very well. And so, yeah. Well, so this is the estimation done, a couple of years ago, and based on recycled concrete, bricks, blocks, and steel slag available, and we estimate it could consume about 400 million tons of CO2 per year. And so you can see, it's really, really effective, technology to, mineralize the carbon dioxide and also produce good products. Well, this is basically, solid technology, and as I said, okay, solid cement, mainly using, tricalcium disilicate, and so then basically use our preconditioning process to make blocks. And yeah, well, advantage, yes, the calcium to silica ratio is low, and the calcining temperature or production temperature is also lower than conventional cement. But on the other hand, for conventional cement, because it's well established technology, so its production cost is very, very low. And well, you can't imagine, and in China, the production cost is only about 100 to 120 yuan per ton of clinker. And also, relatively, the quality is very uniform. And but for those special clinker, and it still take time and take effort to really produce, consistent products. And but of course, the advantage, once the carbonation is finished, and the performance reach peak, and then start to deteriorate, and also poor dimensional stability, and of course, the performance will deteriorate fast. And so, and well, there's a silicon technology. Well, actually, I went to Japan 2 times last year. They also try to market and this technology. Well, they said that they produce gamma dicalcium silicate and mix it with cement and also coal ash and then carbonate and to make brick. Well, I don't really see, the scientific advantage from this mixture or from this portion. And because the gamma dicalcium silicate, as I said, once the carbonation is finished, it does not have the potential to further hydration. And coal-fired thermal, fly ash, if it's low calcium flash, it basically acts as a filler. And, cement is regular cement. And so anyway, they are marketing this technology and they also have done quite a lot of, demonstration. And so, yeah. You know, well, this is Belgium and carbon stone. And so, well, basically, they use 100% just like, to carbonate to produce different products. And well, that's what I said. Yes, technically it's efficient, but on other hand, if we can probably still do more work, on this. Okay, sorry, I put this slide here. And so you can see here, we use some chelate and also some carbonation enhancement additive. And so you can see here and the strength. Okay, typically we can get only about 40 megapascal, and but here we got a 60, 70 megapascal strength. And so, with such a high strength, I think we can, have much more broader applications for this technology. Yeah. And well, so as you can see, carbon mineralization can be very good efficient technology for, carbon dioxide utilization. And on other hand, because the process is very complicated. It involves a lot of physical and chemical process, and think you have to really understand the certain sciences and obey some fundamental concepts, then you can get really good results. And well, of course, still a lot of work need to be done to widely use this technology, and yeah, that's